Good morning, ladies and gentlemen. My name is Jan Horacek, and on behalf of many of my colleagues marked here from many institutes, I would like to present you this topic of predictive modeling of liquid metal divertor. It's a journey from tokamak compass towards compass upgrade. Our motivation is that we think that plasma-facing components based on liquid metals held in capillary porous structures can survive extreme heat fluxes of attached ELMy H-mode plasma in demo divertor. This is a kind of summary of 3 papers. The first one was a design of this liquid metal experiment published in 2018. Then the experiment published by Renaud de Jarnac last year describe the experiment, and the simulations which try to interpret the experiment more quantitatively. So the outline of my talk will be the prediction of extreme heat loads on divertor targets of compass upgrade, ETA and demo in steady state and ELMs. Then I will introduce you to the topic of capillary porous structures wetted by liquid metals, how they survive extreme heat loads. Then I will show you the experiment on tokamak compass with quite high heat fluxes perpendicular to the surface. And this will be the experiment with lithium tin alloy and the simulations of it. And the same simulations applied for compass upgrade with demo-like extreme heat loads of 250 megawatts per square meter perpendicular to the surface. And I will just mention the next steps, which will be its impact on core plasma by Sol piezo or core diff simulations, and then I summarize. Well, the motivation for these liquid metal divertors is here that there is certain engineering limit for steady state water-cooled tungsten, which can survive up to 16 megawatt per square meter, which is shown in this graph by Richard Pitts in logarithmic scales in hours. You can see that at 16 megawatt per square meter, you get about 2000 hours of expected lifetime of these components water-cooled. If you make it from a hyper vapotron, it would be a bit better, but not very significantly. And above 20 megawatts per square meter, you get only 10 hours of lifetime, and then it cracks and perhaps even melts. And this is certainly not acceptable. Last year, I published a paper on the scaling of ETA-L mode without fusion power, so only power given by the heating input power to the plasma. We get already to 10 megawatts per square meter, so quite close to this limit, because the lambda Q decay length is quite small, and here I assumed attached divertor, so radiate only 30% of the escape of layer power. For compass upgrade, similar predictions give us in H mode, the escape of layer power of 5 megawatts will be distributed into area of 2/3 of a millimeter at the outward midplane, which yields to attached heat flux of 80 megawatt per square meter, of course, approximately. This comes from the scaling of Thomas I, the lambda Q in millimeters, with respect to the colloidal magnetic field in Teslas. And the lambda Q decreases in experiments of many tokamaks, and it goes to the value of 1.2 Tesla, where we will be with compass upgrade as well as ETA will be. Prediction by XGC1 code gives quite similar values for those devices. However, for ETA, it yields value much higher, by order of magnitude larger than what one would expect from this simple scaling, empirical scaling. And the reason for this is that the XGC1 code as well as 3D Baud++ predict values about 5-6 millimeters due to large ratio between minor radius and ion Larmor radius. So this is something which cannot be easily verified on small nowadays tokamaks with respect to this device. And this is because the escape of layer increases its turbulence. In such a case, if we believe this, the detached plasma can then reach acceptable values below the cracking and damage limits. If we are rather pessimistic, then we would get values about 100 megawatts per square meter because of this small lambda Q. Then in addition, there are ELM heat pulses, for example, here shown on JET in 2015, how the ELMs melted tungsten divertor on JET. And we know that in future device like demo European reactor will have 4 times higher, or in fact 6 times higher heat fluxes on the divertor. And so either it must radiate a lot of power, or we have to find another engineering solutions for this plasma facing components, or do both at best. So that's why we are interested in capillary pore structures wetted by liquid metals. And here you can see its functionality. The principle of liquid metal is very easy, demonstrated in a so-called kitchen physics. Let's take a plastic foam which you have in your kitchen and wet it by water and heat it by 16 megawatt per square meter flame, which is normally used for cutting metals. And you can see that it's pretty easily cooled by latent heat of vapor, and that's why it never gets above 100 degrees, and so the plastic survives. Of course, in tokamaks we use other materials. We will use, we have used a material boron nitride carbide for the bulk, and just wounded by a mesh made from 0.1 millimeter thin molybdenum wires. This is what we call capillary porous structure, and then it's wetted by lithium tin alloy in our case, or it can be pure tin or pure lithium. And the lithium also then forms a cloud of vapor, which is kind of protective shield, which radiates the energy of the incident plasma out. And of course, the chosen liquid must have boiling temperature lower or much lower than the melting temperature of the wires of molybdenum or tungsten are used. And the vaporized matter is then refilled to the surface by capillary forces. So that's why we have this lithium supply volume, so kind of reservoir, and then through these channels by capillary forces, it just refills back to the surface. And we have demonstrated that it can be done pretty easily even during the ELM rise time and decay time. Here is an overview of some liquid metal plasma facing components where they've survived without any damage. We start in 2009 with QSPA and MK200 device in Russia, where with a surface of 1000 millimeters squared, there it was exposed to heat pulse of 2000 megajoule per square meter and square root of a second by Igor Lublinsky. And it was a plasma accelerator, this thing, and pretty similar plasma to what we have in nowadays tokamaks. And you can see that the heat pulse is even stronger by order of magnitude than what is predicted to be in future ITER or even demo reactor in unmitigated disruptions. So for the heat pulses, it's an interesting plasma facing component. In 2020, there was a nice publication, and also before that, on much smaller areas, steady state, however, steady state heat fluxes of 16 megawatt per square meter and quite reasonable heat pulses have been achieved on plasma gun with lithium capillary pore structure, which was wetted in 3D printed tungsten. On FTU tokamaks for about 10 years or even more, there were experiments on pretty larger limiter, because it's a limiter plasma. So the heat fluxes are order of magnitude smaller for relatively smaller time also, and there is no option for heat pulses. And it was demonstrated to survive pretty well at so large fluxes. Even the influx of lithium into the plasma, or even tin later, was found interesting. The experiments I will show you now was done on compass, where we exposed a very large incidence angle 1.5 years ago, pretty small target on relevant heat fluxes, 12 megawatts per square meter, with pretty small ELMs, because our ELMs are not any bigger. And on compass upgrade, we are going to do the same thing, and that's why we can achieve extremely high heat fluxes which are pretty close to what is one day expected on demo in attached divertor plasma, including the ELMs, which we will have. So this is just a small target, and then we plan in farther future, since 2027, to have much larger area, so to full coverage of liquid metal divertor, so the incidence angle would be small and the heat flux is also relatively smaller. Right. Let's go to the experiment on tokamak compass, where we expose it to these high heat fluxes. So here you can see the geometry. This is tokamak compass with major radius of 0.55 meters, and we put the liquid metal divertor target at the inner strike point, and we placed it such that there is high incidence angle, so that when we insert it a bit deeper into plasma by a couple of millimeters, the angle of attack goes nearly to 45 degrees, so the heat flux gets very high. Here you can see how the plasma flew above our divertor probes, which measure the parameters of the incident plasma, including ELMs, because they have time resolution of 1 microsecond and 3 millimeters in space. Here you can see image from the visible camera, where the vaporized lithium and sputtered lithium radiates in red color. That's the neutral cloud. Then the lithium plus becomes green, and it's pretty nicely visible behind the target. There is when we insert the target not very deeply, the plasma drags the lithium behind the target, and we see some green color here. And once we put it deeper into plasma and the pressure of lithium increases above the plasma pressure, because the temperature of the surface increased strongly, we see that the lithium penetrates in front of the target, which is visible by the camera. Here you can see the photographs before the experiment and after the experiment. You can see the area which was exposed to plasma. It changed the color. Otherwise, there is no visible damage of the capillary pore structure mesh. And we also observed no droplets expelled from the surface. Here you can see ELMy H-mode scraper flare profiles. In blue color is without the liquid metal divertor inserted, and in red is with the target inserted. And you see there is no visible difference on the electron temperature profile at outer midplane, and also heat flux. The heat flux is even higher, so certainly the target did not cool the plasma. We saw a similar, we could drive similar conclusion from the extreme ultraviolet radiation. So this is without the liquid metal target, and this is with the target included, and you see no visible difference in the pattern on radiation and also the total amount of radiation. There's no traces of tin inside the plasma which we could have observed. The postmortem LIPS analysis presented in this paper show no or very low traces of tin on 14 samples of screws on the divertor. So now let's go to the simulation of this vapor shielding. So we built a three-dimensional model of heat conduction and vapor shielding. Unfortunately, the heat conduction dominates the surface temperature, which means that the vapor shielding was pretty weak in our experiment. The heat conduction equation is pretty simple. We had to assume that the heat conductivity in the capillary pore structure is equal to the lithium tin conductivity, because it's perpendicular to the surface. The input to the model are, of course, data from divertor probes in ion saturation current and temperature. It means density and parallel heat flux, and we measure it with extremely high frequency, even the temperature with microsecond. So that's how. So here is how we calculate the total amount of released lithium, we take the deuterium influx, which is the ion saturation current density, and multiply it by this 1 minus prompt redeposition, which we believe is really 0, which I will explain on the next view graph. And the reason is mainly that the mean free path is much larger than the ion Larmor radius, so there is no chance for the ions to return back to the surface. And this is what we multiply by the thermal sputtering, which is a function of surface temperature calculated from the heat conduction mainly, then plus the preferential sputtering, which is dependent on temperature of the plasma, plus the vaporization, which is given by the surface temperature again. And this is in fact shown here, the evaporation rate, which rises very strongly exponentially with the surface temperature in degrees, which is calculated either for lithium or lithium tin alloy or tin itself. The evaporation cooling is either local, which is given by the latent heat of vapor, because each particle just loses 1.4 electron volts of energy, plus vapor radiating shielding, which should be quite high, because this cooling energy per each released atom is pretty high. It goes from tens up to hundreds of electron volts, depending on the electron temperature of the incoming plasma. However, it spreads into very large area. In fact, area which is 100 times larger than the hotspot, which is only 5 millimeters large, and the radius of mean free path ball of lithium radiating cloud. So it means that this energy, in fact, decreases by 2 orders of magnitude, and that's why the lithium vapor shielding is pretty negligible in our experiment. I will show you in a moment. To know what's the mean free path of the lithium ionization and excitation, we had to perform bit1 simulations by David Sakaya. The input to this code were temperature and density from probes, and also the amount of released lithium from the previous simulation. So it had to be done somehow in the loop, these two codes together. And here you can see the results. So this is the density in the cubic meters in logarithmic scale. And this is colloidal distance from the target in logarithmic scale. So you can see that near the target, there is only lithium, and then it decreases at about 6 centimeters away from the target. It starts to decrease. And here, close to the target, is by 3 orders of magnitude larger than the density of deuterium plus. And there is also some neutrals of deuterium. And we included also carbon and lithium plus and double ionized lithium. Here you can see the excitation and ionization rate. So at about 6 centimeters from the target, the intensity of radiation of the ionized lithium should decrease by a factor of 3 and down by order of magnitude that 10 centimeters away. And this is pretty close to what we measured with a visible camera, that there was a radiating sphere of 12 centimeters diameter. So it's a pretty good match, taking into account that we have a lot of unknowns in the code. So the 3D model of the heat and conduction vapor shielding shows here the main results. Here, this is the infrared camera image. This is magnetic shadow. So the plasma was exposed only to this top of the target. The plasma was going like this. So it's a shallow angle and a pretty high angle up to 40 degrees. Here, in this case, 30 degrees. And the maximum values across these two images are shown here in time. So you can see that they correspond very well, the heat conduction model and the infrared camera. Even the details of the ELMs you can see here. And in order to resolve them in the model, we had to assume pretty strong surface thermal insulation of the capillary pore structure, about 1 megawatt per square meter in Kelvin. If we didn't do this, the temperature would rise only by 3 Kelvin. We don't know really why. The calculated vapor shielding in this case have been only 0.15 megawatt per square meter, because it's spread over this 100 times larger area than the hotspot itself. And at the hotspot, it was cooled by the latent heat of vapor, which was up to 1 megawatt per square meter, not larger. than this. In fact, it would start to be dominant at about 900 degrees Celsius, but we couldn't reach higher temperature than this. Here you can see a survival of downwards disruption, vertical displacement event. During this VDE, the plasma lighted the whole vessel like this. You can see the target here. I can show you a video how the plasma was going down within a half a millisecond during this disruption event. In fact, it delivered about 25 megawatts of power near this area because it just lost 5 kilojoule of its energy within this short time. The surface temperature rise by 150 degrees during this short time, which is also visible here by the infrared camera. It was not exposed strongly, only this tiny surface, and only 30% of the parallel heat flux went to the surface. But it was at least interesting to see that it was not damaged by this disruption. Right. So now we are going to the simulation for compass upgrade with demo-like extreme heat fluxes, and I will show you just those simulations. So firstly, to introduce you to this new European tokamak called Compass Upgrade. It's located in Prague, Czech Republic. It's similar to Alcator C-mode in some way. It will deliver very high power density to the tungsten wall and divertor, and we expect first plasma in 2023, maybe because of coronavirus a bit later. It will be a divertor tokamak with 5 Tesla and 2 megaamperes. We will reach these parameters in 2025. The reason for so high values is that we will use vacuum cryostat such that we can cool the copper coils to minus 200 degrees Celsius and so reach so high magnetic field and current. And also we will bake the vessel up to 300 or even 500 degrees Celsius, which is quite important for the liquid metals, which I explain you here. That here we will introduce a liquid metal target in the beginning of 2025, hopefully into this outer divertor region, outer strike point region of compass upgrade, and again at very high incidence angle. All the vaporized and sputtered lithium would then go to the vessel, but because the vessel will be baked to these high temperatures, it vaporizes off again, and then it will condensate somewhere on the cold condenser, which we will place somewhere in the chamber, maybe even as close as possible to the target itself, or maybe at other places. And in such a way, we will protect the lithium to penetrate and tin to penetrate inside the main plasma. We hope so. It's a similar way as it's done on T11 in Russia. How to do the simulations of the liquid metal operation? We will use again the data from the divertor probes from Compass, and we just rescale them to this larger machine Compass upgrade. And we will do it like this, explain here, that this is the input to the liquid metal divertor simulation, just how to rescale it. We measure it with extremely high frequency, up to 1 microsecond, even the temperature, thanks to the ball pen probes. And here you can see the result. So this is in space coordinates in millimeters with respect to the time. And here it's shown for 1 ELM. So this is inter-ELM period and 1 ELM shown here. And this is heat flux in parallel heat flux in gigawatts per square meter, which we expect. This is temperature in electron volts, ion saturation currents. It means the deuterium flux on a 3 millimeter squared probe area. And this is density in cubic meters. So these are measured values from Compass, rescaled for Compass upgrade in such a way. Firstly, we assume that the time scale will be the same because the parallel connection length divided by the sound speed give you more or less the same value. So the time scale of ELMs will be the same. Then we have to rescale it in space by a factor of 2 because we will have much larger flux expansion on Compass upgrade. So for this spatial coordinates, we use Fiesta to map it from outboard midplane to the divertor. And on outboard midplane, we generated the I function, which is this purple line from where we took the lambda q value of 1.3 millimeters from these scalings and use METIS to derive these, to evaluate these scalings. Of course, we use attached plasma on the divertor. We don't think about detachment in these things. And then the temperature will be only 10 electron volts, which comes from bit1 simulations. So we had to divide the temperature from compass by factor of 6, and in the opposite we have to multiply the ISAT by 36 in order to get heat fluxes, which we assume will be there, calculated from these profiles. During the ELMs, we need to do another treating of the data, because we know what will be the parallel energy density during the ELMs, about 340 kilojoule per square meter. So constructed space-time signals keep all the filaments and cross correlations. So now we took those data and put it into this model. So again, plasma flow from this direction at high incidence angle. The surface will reach up to 700 degrees Celsius, and there will be also heat conduction into the bottom of the target, which we assume to be cooled by probably by water. And you can see that the cooling will be about 15 megawatt per square meter, and otherwise the surface temperature will be dominated by sputtering and only very weakly by evaporation, because the surface temperature will be relatively weak. So this is for ELMy mode, which you could see here summarized. 14 target with 14 target, we expect temperatures about 1500 degrees Celsius, and the conduction will deliver only 70 megawatt per square meter and evaporation 50, and sputtering 70. So here we would release tin particles. If we assume liquid lithium, tin or tin alloy, then we would expect much larger sputtering ratios, but similar parameters for the heat cooling. Here you can see my summary, and I thank you for your attention. We plan for next step to simulate the influence of this released lithium on the plasma by Solpies and Cordiff, but this is a topic for another presentation. So I thank you for your attention, and please questions.